The pivot optimizer controls the pivot center and end pressure directly, removing excess pressure and thereby minimizing the energy use of the system. In addition, it also monitors other key pumping parameters. The pump inlet pressure is also monitored. The inlet pressure is then compared with the allowable operating range of each specific pump. If the pump inlet pressure drops too low, then the pump differential pressure drops and the efficiency of the pump is reduced. If the pump inlet pressure drops further, then the pump starts to cavitate and permanent damage is done to the pump. Cavitation sounds as if the pump is pumping small stones. In reality, this is vapor bubbles that form from the very low pressure and then implode against the impeller. When the vapor bubbles implode against the impeller, it erodes away small amounts of metal and permanent damage is done to the impeller. The impeller ends up with a large number of holes in it. The pump outlet pressure, flow rate and electrical power is also monitored. The inlet pressure, outlet pressure and flow rate is used to calculate the hydraulic power delivered by the pump. The ratio of the hydraulic power to the electrical power absorbed by the motor is the combined pump and motor efficiency. A good pump efficiency is around 80%, while a good motor efficiency is around 92%. When you combine 80% efficiency with 92% efficiency, you get a good overall pumping efficiency of around 74%. If the efficiency is lower than this value, it indicates that it's either an older pumping design or it's the incorrect size pump for that particular application, or the pump has worn out. When we monitor the efficiency of the pump and find that the efficiency is low, we can then advise the farmer to either overhaul the pump or to change the pump for a more appropriately sized pump. The pivot center pressure is subtracted from the pump outlet pressure to give the total pipeline pressure drop. The change in elevation from the pump to the pivot is then subtracted from this to give the pipeline friction pressure drop. A good friction pressure is in the order of 1/4 to 0.5%, but a lot of systems have been designed to have around a 1% friction drop. Some systems have even got higher friction drops, and we've measured friction drops as high as 2 and 3%. When the friction drop is this high, it means that you're wasting a huge amount of energy through pipe friction. By monitoring the data, we managed to advise the farmers to change their pipelines to larger pipelines, thereby reducing their pipe friction and achieving higher energy savings. By making a combination of changes, which includes the optimum efficiency pump, low pipeline friction, and control of the pivot center and end pressure, we can achieve savings between 50 and 75%. Frequently, clients are limited by their transformer capacity. They either want to apply more water to an existing area of land or want to increase the area under irrigation. However, the transformer is too small to allow more pumps to be run or to increase the capacity of the existing pumps. Upgrading a transformer is very costly because Eskom charges a large deposit. It also takes a large amount of time. Once a transformer is upgraded, it only gives you the right to spend more money on your Eskom bill every month, so it is a very poor overall solution. In most cases, by selecting the correct pump and motor for a particular flow rate, we can achieve a dramatic saving in the kVA demand on the transformer. We can also optimize the combination of flow rate and pumping hours. This means that we might pump for a slightly longer period of time at a lower flow rate, but overall this allows more pumps to be run at the same time, and so we can achieve a higher application of water. For example, if there are 2 pumps, each drawing 55 kVA installed on a 100 kVA transformer, then it means that you can only run 1 pump at a time. This results in 45 kVA of unutilized capacity on the transformer. If in our example, each pump delivers 200 cubes of water per hour, then in a day, the system can only deliver 4,800 cubes of water. Even if we cannot improve the pump efficiency, we can reduce the flow rate of each system by 10%. This will result in the kVA draw of each pump reducing from 55 kVA to 50 kVA. This will mean that both pumps can be run at once. In this example, the individual pump flow rate drops to 180 cubes per hour. However, both pumps can be run at once, meaning that transformer can now deliver 360 cubes per hour. This gives a daily flow rate of 8,640 cubes. This is an 80% increase in volume that can be pumped by that transformer in a single day without having to make any changes to the actual pumps themselves. I'm standing at the pump house for Pivot 2 on My Hill Farm. This is the original pump and motor for the Pivot. It is a 30 kilowatt motor, and when it was running the Pivot, the motor was drawing 22 kilowatts. We tested the complete system and found that the pump and motor were completely oversized for the flow rate required by the Pivot. This is quite typical of many systems that we test. After analyzing the data, we determined that the best pump and motor for the flow rate would be this unit over here, which runs off a 9 kilowatt motor. That's a reduction from a 30 kilowatt motor drawing 22 kilowatts down to a 9 kilowatt motor. When we are running the 9 kilowatt motor with the pivot optimizer and a variable speed drive, the system draws an average of 5 kilowatts. This is a reduction from 22 kilowatts, or a saving of 75%. When the pivot is facing uphill, you can work on a higher power consumption, and so the maximum demand is around 9 kVA. But still, this is a reduction from a 30 kVA maximum demand. This means that more pumps can be placed on the same transformer without overloading the transformer. Our client was highly skeptical that a 9 kilowatt pump and motor would be able to deliver the same flow rate and pressure as the original 30 kilowatt unit. That's why you see both systems are still plumbed in, so that if we were wrong in our predictions, the client could go back to the original pump and motor. Luckily, this proved to be unnecessary, and the 9 kilowatt pump and motor delivers more than enough flow rate and pressure for the Pivot. This original pump and motor was also used to deliver water to Pivot number 1. When it was delivering water to Pivot 1, the actual power draw was 28 kilowatts. We performed a complete system optimization and determined that another pump and motor would be more suitable, and the location of the pump and motor could be optimized. So we've moved the pump and motor for Pivot 1 from this pump house to the Slurry Dam pump house. By moving the pump and motor to a different location and using a smaller pump and motor, we reduced the power consumption from the original 28 kilowatts down to 17 kilowatts. Then, by fitting the Pivot optimizer with a variable speed drive, we reduced the average power consumption from 17 kilowatts down to 11 kilowatts. Remember that this is a reduction from the original 28 kilowatts, so the overall power saving on the system has been more than 60%. I'm standing at the center of Pivot 3 on My Hill Farm. The pump for the system delivers water to the Pivot as well as a pod system. The pods need to be run during the day because they need to be moved around every 4 hours. Because of the scheduling of the system, the changeover from pods to Pivot and Pivot to pods needs to take place at night or in the very early hours of the morning. We don't want this to be done manually because that would require somebody to come out at night. So we've automated the system to change over according to a timer. The system has got a main control box which controls the timing of the Pivot and pods. During the day, it will open the valve for the pods, turn on the pump, run the pods at the correct pod pressure, and then at night it will shut off the pump, close the pod valve, open up the Pivot valve, turn on the pump and run the pump at the correct pressure for the Pivot. At the moment, the system is running the pods, and I can also run it manually, so I can turn off the pods now. The pump turns off immediately and it will wait 1 minute before closing the valve to the pods. That 1 minute is just to allow the pump pressure to reduce before closing the valve. I'm starting the pivot up in manual mode by flicking the switch. The first thing that happens is it sends a command to the valve, which is opening now. Once the valve is open, then it will start up the pump, and you'll see a light coming on here to indicate that the pump is running. There, the light has come on, so now it's running the pump. Once water pressure arrives at the pivot, then the main control unit in the pump house will set the correct pivot center and end pressure. This is the pump for pivot 3 on My Hill Farm. Shockwave Engineering selected this pump for this particular pumping application because it manages to achieve very high pressures at very high efficiencies at moderate flow rates. On average, this pump draws around 12 kilowatts of power, despite the static head from the pump house to the pivot being 80 meters. I'm standing at the center of Hlogoma pivot belonging to Murray Turner outside Underberg in KwaZulu-Natal. Shockwave Engineering tested this pivot as well as a supply pump and pipeline. Initially, the power consumption was 40 kilowatts. Shockwave Engineering analyzed the data and found that the pump was incorrectly sized for the flow rate, the pump was worn, and the pipeline was far too small. There was also excessive pivot pressure. After doing a thorough analysis, we advised Murray to change the pump and motor, upgrade the size of the pipeline, and install the pivot optimizer with a VSD. After doing that, the power consumption dropped down to 17 kilowatts, which was a saving of 56%. In conclusion, by optimizing the overall pumping system, very large energy savings can be achieved. More water can also be pumped by the same transformer.